Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you. And this is the NPTEL MOOC course, which is the TQM2 course. And as you know, this is for a total duration of 8 weeks, and we are going to start the 21st lecture. That means we are almost halfway through, and we are starting the fifth week, first lecture. So, if you remember, we were discussing about the concepts of different factors, and if you and again I will repeat these examples time and again. We did one example where power and the effect of different type of etching problem was there. Then in the case of battery, the temperature and the material problem was there. Then was the aluminum smelting, and then we gave the formulas that given more than 2 factors, you will basically have factor A, B, C, then the combination of 2 at a time, A, B, B, C, A, C, then taking 3 at a time, A, B, C, you can have basically the total sum of squares, the individual factors sum of squares, then the error terms, and obviously the factors would be in the combinations, as I said, A, B, C separately, A, B, B, C, A, C taken together, and then combination of 3. And if you go to 4 factors, obviously they would be individual A, B, C, D, then combination of 2, combination of 3, and then 4 combined together. And then we also understood that if the number of so called observation of factors, I will not use the word observation factors, for A was small a, for B was small b, for C was small d, C, and for D was small d, and the total number of observations was small n, then the total number of set of observations for the whole experiment will be A into B into C into D into N, and combining that you can find out the different degrees of freedom for each factors individually combined together, 3 together, and so on and so forth, plus the degree of freedom for the error terms. Then based on the total sum and the degree of freedom, we found out the mean squared errors. Using the mean squared errors for the total, for the factors, for the errors, we found out the F statistic, and then we combined that, said that whether they were significant or non significant depending on the level of significance. Now continuing with the last problem. So, they were basically 3 factors A, B, C, as I said, and the total observations was small n. So, if you are trying to find out the sum of the square of the totals, which would basically be, if you continue only concentrate on the formulas, the values would be coming out automatically. So, what you have is, so we are sum of the squares, that means you have to find out the squares. So, here the first term is y square, and for each cell, so how many cells are there if you consider a matrix of higher dimension, more than 3. So, the first cell would basically, the first cell means the factor corresponding to the first cell would be termed as I, the second would be the J for the B, K for C, and L would be basically for N. So, I is changing from 1 to small a, J is changing from 1 to small b, K is changing from 1 to small c, L is changing from 1 to small n. And if I consider the dots, so technically the dots would be, if it is the first dot, it means that I am summing up for all the a's, small a's, which is for factor capital A. If the second dot is there, which means I am summing up for all the b's, small b's, for factor B, capital B. If dot is there for the third place, it means I am summing up for all the small c's, which is for the factor capital C, and so on and so forth. So, it can go for like to D, to E, to F, and so on and so forth. And the last one obviously would be corresponding the fact that you are summing it for all set of observations. So, if you have the sum of the squares, the value of the sum of the squares for the total corresponding to the case. So, this was one element y square I j k l, and y square 4 dots corresponding to I, corresponding to J, corresponding to K, corresponding to L, divided by obviously total set of observations would be, as I said, A, B, C into N. So, based on that I find out sum of squares of total is 336.625. So, then if I go to the factors. So, they would be SS suffix capital A, SS suffix capital B. So, if we name them, so here it is carbonation, which is factor A, pressure, which is basically factor B, and speed, which is factor C. From there, if I want to find out the sum of the square of the errors, so here it will be y square I triple dot, because I am summing up for keeping I at fixed at one level, I am summing up for all j k l. Similarly, when I go to the second one, it will be dot for the first place, j for the second place, and third and fourth would be dot as mentioned here. So, if where I am circling, please make a note. If I go for the third factor, which is C, which is the pressure, it will be dot dot k and again a dot. So, dot dot k again a dot, and if I consider the term which is to be subtracted, it will be y square 4 dots divided by A B C n, which is whatever. I will try to utilize another highlighting color. Let me circle it. So, highlighter may make it dark, sorry for that. So, this is what we had, A B C n. Now, it will be again y square triple 4 dots A B C n. So, these are matching, this one and this one. So, once you have this, the values which you have, some score total squares is 336.625 for A factor A, it is 250, I will not repeat the decimal part, it is 252. For the B part, B factor is 445, and C part, which is speed, is 22. Now, I need to find out the combination of AB, which will be carbonation and pressure, then BC, which will be pressure into speed, and AC would be carbonation into speed. And finally, I need to find out all the combinations, carbonation, which is A, pressure, which is B, and speed, which is C. So, let us see. So, here it will be SSAB. So, I will read it. To calculate the sum of the squares for the two factor interaction, as I just mentioned, we must find the two-way cell totals. For example, to find out the carbonation and the pressure, which is, or the AB interaction, as I mentioned, we need to find the total for all the cells of A into B. So, which is basically y I j dot dot. I am basically keeping I and j fixed at any particular level, starting I is equal to 1 to small a, j is equal to 1 to small b, but summing up for all the c's, small c's, and summing up for all the small n's. So, as already discussed, so using this equation, we find out sum of the squares of AB, which is carbonation and pressure. The value comes out to be about 5.250. I am mentioning the decimal part here. Then if I go for the pressure and speed, which is AC, then I have the value as 0.583, and if I go to the, this AC is basically, sorry, the first and the third, which is carbonation and speed, and then I go to the BC interaction, which is pressure and speed, the value comes out to be 1.042. The calculations, the formulas remain the same, only you have to put it and try to understand that. And always remembering that when you make the tables, on the leftmost column would be the factors, with the factors being mentioned as A / whatever the factor actually in words it is. Like in, say for example, in this example, A means carbonation, B means pressure, C means pressure and speed. So, you write it down. The second last value in the first column would be the error term. So, double check that the sum of all the, in each cell, when you are doing the total sum of squares or the errors, sum of all the errors would definitely will be the total errors. You can double check in both ways, by first finding out the total sum of square errors, then finding out the individual and the combined one, and then utilizing that to find out the error terms, or back calculating to find out the error terms as the error terms matches, sum of the squares matches in both this case. So, as we were discussing, the sum of the squares would, if you have the first column written with all the factors, then the second column with the total sum of squares. So, total sum of squares, and what I mean is basically they would individually be for A, B factor, C factor, combinations of A, B and C taken two at a time. The last one would be for the combination of the three taken all at a time, if considering the three factors. The second last, again I am repeating, would be the errors, and the last one would be the total sum of square of the errors. So, obviously you can double check, as I said, finding out the sum of all the errors plus the error term would be, sum of the squares would be equal to the total sum of squares errors, and then you have basically the third column would be corresponding to all the degrees of freedom. So, that you have to basically make a note that how you will find out, considering the total number of factors for A, capital A is small a, for capital B is small b, capital C is small c, and so on and so forth, and the total number of observations being small n. And then you divide. So, you complete the first column, second column, third column. In the fourth column, you will basically find out the mean square errors, and then in the fifth column, considering the ratios of the mean squares, you will find out different on the F statistic, and then utilize that to solve the problem. So, you basically have a chart, and in the chart you plug in all the values to calculate the the values. Now, as I mentioned that you have the SS suffix AB as 5.250, SS suffix AC. I will be only using A, B, C as the factor name rather than going into detail. So, it will be much easier for us to proceed fast, and also you are in tune with the word A, B, C which I am being using time and again, and SSBC is 1.042. So, now I go to the next stage. What do you mean by next stage? Is basically I need to find out the combinations of A, B, C. So, if it is combinations of A, B, C, it will basically mean that rather than keeping the cell value for all the values of initially, say for example, it was A, B, what we did is that we found out for all C's and all N's. Now, it is A, B, C. So, it will be for one specific value of A, one specific value of B, one specific value of C, which means it will be suffix I, that the sum of the squares will be suffix I, J, K, and the fourth dot would imply that I am finding out for all the set of observations as it is given. So, if I do, so let me change. So, if I do, the value comes out to be 1.083, and the subtotal basically for ABC is calculating it, the values comes out to be 328.125. From that you can find out the sum square of the errors. So, this is the errors which I am finding out is 8.50. So, now basically I will have a table. Before reading it, I will go first to the table and then come back. So, if you note down the first column where I am pointing out, I am writing number 1 means column. It is all related to, say for example, factor A, factor B, factor C, AB, AC, BC, ABC, error total. Check the total sum would be exactly equal to the sum of all this. So, this is column number 2, which is the sum of the squares. Then you have the degrees of freedom, which is column number 3. So, here also you can check the degrees of freedom sum. Then you have the mean square, that means you divide column number 2 by column number 3. So, say for example, you are taking this value. So, 1.042 divided by 1 comes out to be 1.042. So, similarly 22.042 divided by 1 becomes 22.042. Then if you find out, say for example, 252.750 divided by 2 comes out to be 126.375. So, once you have the mean square in column number 4, then you have the ratios of the mean square giving you the F values, and then depending on the P values on the level of significance, you can basically say whether you agree with the hypothesis, disagree with the hypothesis. So, it can be extended for A, B, C factors and so on and so forth. So, the ANOVA is summarized in table 5.14, which is here as I am mentioning. We see that the percentage of carbonation, which is A operating pressure and the line speed, basically which is factor B and C, significantly affect the final volume. The carbonation pressure interaction F ratio has a P value. P value depending on the level of significance which I have is basically 0.0558, indicating some interaction between these factors. The next step would be an analysis of the residuals from this experiment. We leave this as an exercise and one can solve it very simply to find out what are the results. To assist in the practical interpretation of this experiment, we have figure 5.16, which presents the plots of the 3 main effects and the AB, which is basically the carbonation and the pressure interaction. The main effect plots are just graphs of the marginal response averages at the level of the 3 factors. So, at the 3 factors I want to find out the marginal effects. Notice that all the 3, which I will come to that, notice that all the 3 variables have positive mean effects, that is increasing the variable moves the average deviation from the fill target and upwards. So, it basically keeps increasing, positive effect. The interaction between carbonation and pressure is fairly small. So, obviously, the line would be almost horizontal, basically giving you the impression, and obviously that would be true, the tan of that angle or divide dx or the rate of change of that function value with change of these factors would be almost 0, because that is why the effect is almost 0. Because the company wants the average deviation from the fill target to be close to 0. So, obviously, the average deviation should be as the dispersions or the variances would be 0, which means the average deviation from the fill target to be as close as 0, which I am just repeating. The engineer decides to recommend the low level of operating speed of 25 and the high level of line speed, which is 250, which will maximize the production rate depending on the answer we are getting. And figure 5.17 plots the average observed deviation from the target fill height at the 3 different carbonation level for this set of operating conditions. Now, the carbonation level cannot presently be perfectly controlled in the manufacturing process, and the normal distribution shown with the solid graphs may be a deviation, but we will still follow that, which approximates such that we can find out the variability in the carbonation levels present experimentally. As the process is impacted by the value of the carbonation level drawn from this distribution, the fill heights will fluctuate considerably. This variability in the fill height could be reduced if the distribution the carbonation level was followed the normal distribution. So, obviously, it would not be normal, but we will still consider that to be true. So, reducing the standard deviation the carbonation level distribution was ultimately achieved by improving the temperature control during the manufacturing process, as that a best fit could be observed accordingly. So, if I see the graphs now what I am coming, so I will go slowly in trying to explaining that. Consider you have the average fill deviations. So, I am trying to find out the deviations with the dispersions with respect to factor A, which is in figure as I am pointing out. Let me highlight it. This is for A and factor is A. The graph is named A, not the number of observations. For pressure B, the graph is B, and you have again along the y axis you have the average deviation, and for diagram C, it is basically line speed, which is factor C, and here again the average field deviation. And when I am considering the combinations of carbonation pressure is basically the factor B, but at 2 different pressure levels. So, at 2 different pressure levels, which is 25 psi pound per square inch, and another way being 30 psi, the values you will basically get would give you an answer. So, in this case, in the first diagram which I am highlighting, the rate of change is quite high, it is almost linear, even though for percentage carbonation changing from 10 to 12, 12 to 14, they are not, because it is more steeper from 12 to 15 than from 10 to 12, but they are almost linear. Similarly, if I consider the pressure one, it increases from 25 to 30, while the average fill deviation changes from 2 to almost about 4.75 or 5. And if I consider the line speed changing from 200 to 250, the average fill deviation changes from 2 to almost about the same value as you found out in the pressure. So, in these 2 diagrams, the change, the rate may be different, but the change in the value of the y axis, which is average fill deviation, is almost the same. Now, when I find out the carbonation pressure interaction for 2 different pressures, I find out that in the case when you have 30, so exactly what we have drawn, and the value of 25 psi, what the equations would basically mean, that the initial rate of increase from 10 to 12 for different psi's is slower in rate than when you increase it from 12 to 14, as I found out in both these cases. So, it means that the main effect of the interaction plots, for example, in diagram A is the percentage of carbonation, which is for factor A. The second one is pressure B, which is basically the factor B, and the diagram C is the line speed, which is factor C, and then I find out the carbonation and the pressure combinations. Based on that, we have the diagram D as I explained. Now, figure 5.17 as shown basically shows the average field height deviations again for high speeds and low pressure for different carbonation levels. So, as I check, you will find out that you take different values. So, at lower values here, it is a deviation for which it is very small, and we would definitely like the deviation to be as small as possible. So, when we plot the percentage carbonation and we are trying to find out the improved deviation distribution, the percentage carbonation and the distribution the percent carbonation in two different cases, and then we find out that considering normal distribution, you will be able to find out the deviation has really decreased. That is what our aim would be. So, we try to find out the best combinations of for these three factors, which will give the maximum amount of throughput. If throughput is not basic, throughput means the average, and if our concern is to reduce the deviation, obviously we will try to basically concentrate on the standard deviation and the variance. And one thing we should remember that we will underlying we will always consider normal distribution to be true, which may not be the case in the maximum of the examples. And another example is that we are always considering the sum of the square of the errors, which intuitively would not is the best way of trying to find out how to minimize the error, because square means that we are trying to find out the variances, and trying to minimize the variances would also mean that we are trying to find out the dispersion to be the minimum. Now, you want to find out or study something about the fitting response curves and the surfaces. So, the ANOVA always treats all the factors in the experiment as if they were qualitatively or categorically designed. However, many experiments involve at least one quantitative factors. It can be useful to fit a response curve to the level of quantitative factors, so that the experimenter has an equation that relates the response of the factors and basically builds up the model accordingly. These equations might be used for interpolation and better prediction, that is for predicting the responses at the factor levels, such that we are able to understand the effect and the relationship of the factors to the maximum possible extent using quantitative equation modeling. So, let me read it. For predicting the response at the factor levels between those actually used in the experiment, when at least two factors are quantitative, we can fit a response curve, because in that case we will basically utilize the x axis and the y axis for those factors and then basically plot the curve accordingly. So, we can, so let me again continue reading it with your due permission. We can fit a response surface for predicting the various combinations of the design factors, and in general linear regression models are used to fit these models, because linear regression would be the best way of trying to basically find out the quantitative relationship which we are thinking about. So, let us consider an example in detail. Consider the battery life experiment which you have already discussed. The factor temperature is quantitative and the material type is qualitative. So, material type can be say higher level of say for example lithium, lower level of lithium, considering lithium batteries, but the temperatures are if you remember, the temperatures are quantitative in nature, and because those are values either in centigrade or Fahrenheit. Furthermore, there are three levels of temperature. Consequently, we can compute a linear and quadratic temperature effect to study how temperature affects the battery life. So, figure 5.15 or table 5.15 represents the linear and quadratic effect of the temperature, and B represents the main effect of the material type factors. So, let us recall that the material type is a qualitative factor with three levels. So, consider the terms as A n to B, another would be A square into B, depending on the level of significance we think A would have, which would basically denote the interaction of the linear and the quadratic type, where A and B it is basically a linear relationship between A and B. If it is A square into B, it is basically a quadratic relationship between A and B. And again, if it can also be put like A into B square also, but then the quadratic relationship in words remains the same, but the effects would be different, because in the first case you are squaring A value to A square, in the second case you are trying to basically squaring B to B square. So, the p values indicate that what is the relation indicates that A square and AB are not significant, whereas in the term that we can, whereas a square b terms is significant. So, obviously, you have to basically pass judgments accordingly. Often we think consistency in a model, and many statistical models builders rigorously follow this principle. However, hierarchy is not always a good idea. So, if you want to basically have an hierarchy that okay, a square b would be the of the highest effect, then ab squared would be the next effect, then would be ab, so on and so forth. So, that may be true theoretically, but what is the practical essence? It is very difficult to find out. So, however, hierarchy is not always a good idea, and many models actually work better at prediction equations without including the non-sequent terms that promote the hierarchy. For more information, let us see the temperature text material for this chapter. So, the computer output also gives model efficiency. So, what we have is basically in this equation the level of temperatures have been denoted by as A as minus to the lowest level, 0 at the middle level, and 1 plus at the higher level. So, when the temperature levels are consecutively at 15, 70 and 125. So, basically I am trying to equate the quantity part to the qualitative part in a way using as plus 1, 0 and minus 1. The variables are coded indicator variables that are defined as follows. So, they would basically be the design experts comments for this experiment, and we would assume that the temperature is qualitative and the material type is also qualitative. That means, we are converting the temperature from the quantitative scale to the qualitative scale. But obviously, your question would be that when we are converting these temperatures of 50, 70 and 125, so shouldn't it be, say for example, because the difference between 50 and 70 is basically about 55, and the temperature difference from 70 to 125 is also 55. But what if, say for example, the temperature differences from 70 it is now to 225. So, how would we do that? Obviously, the scaling factor has to be brought into the picture. So, rather than plus 1, we may be tempted and utilize the value of plus 2 to signify the higher level of quantitative to the qualitative conversion which we are trying to do. The ANOVA in table 5.15 shows that the model sources of the variability have been subdivided into several components. The components A and A square represents about removing non-sequent terms or factors from a model, but in this case removing A square and AB and retaining A square B will result in the model in different hierarchies which may not be actually possible to understand. The hierarchy principle indicates that if a model contains a higher order term such as A square B, it should be contained, it should also contain all the lower order terms also. So, which means that in case if the step jumps for the quantitative part of our equal values, then trying to basically do a one-to-one mapping from the quantitative part to the qualitative part would be easy. But if the jumps are different values or different quantums, so say for example, jumping from in the first stage is jumping from 10 to 20 and another second stage is jumping from 20 to 50, then trying to basically find out plus 1, plus 2, plus 3 may not be the actual answer for converting the quantitative to the qualitative concept. So, hierarchy promotes a type of internal way of trying to model it. So, there are prediction equations for the battery life in terms of the actual factor models. So, we should notice because material types is a quality factor, hence it is easier to convert the quantitative to the qualitative one rather from the qualitative to the quantitative one. So, with this we will end the 21st lecture and continue discussing more about this quantitative and quality part later on in the 22nd and 23rd lecture and further on. Have a nice day. Thank you very much.